And today it is my pleasure to announce Kyrylo Kuchynskyi with a talk about concentration inequalities for measure-valued solution to stochastic differential equation with interaction. Please, Kyrylo.
Hello, everyone. Yes, you can see my screen. Yes, no.
Yes.
Yes. My topic will be about the solution to the stochastic differential equation with interaction, and how some functional inequalities evolve with this solution. Let's start with the definition. What is the stochastic differential equation with interaction? They were introduced by Andrei Anatolyevich Zhirakovtsev, and they describe how the infinite system of particles evolve. The main object is the single particle x ut at time t. They indexed by u, and u is a starting point. And all coefficients also depends on measure mu t. Measure mu t is push forward of some initial measure mu zero, and because of this measure mu t, we have interaction. We have some initial distribution, then we have push forward of this measure, and such system describe evolution with interaction. Here we have running motion bt, that d-dimensional, and because our arguments of coefficients is measure, we need some space of measures, and for example, we can consider space of measures with finite second moment, and both coefficients depends on position itself and measure mu t. And more explicit coefficient which show why we actually have such interaction, we can consider, for example, a coefficient of the drift coefficient, and consider it in this form of integral or some function phi. And in the argument of this function, if we have current position xut minus v, but because we define mu t as a push forward, then we can actually write it as integral over all other particles which we actually I can I think we can, yes, we can write this integral over all particles indexed by y over some initial measure mu zero. And in the most simplest example, if we consider phi just identity mapping, then we have the current position xt of particle minus it's the center of mass. So the whole idea about stochastic differential equation with interaction that all coefficients depend on the position of all other particles in the system, and to provide some more explicit examples, we can consider this without any diffusion argument. We can set sigma is equals to 0, and consider such a drift with function f. And we can start with measure mu0, which is a discrete measure, and we have some starting position u1, uk, and we want to describe how these particles evolve with time. And the stochastic differential equation with interaction is actually the way how we can describe it. And the position, if we have n position and particles which started from y position, then their law can be described like that. That we have the same weight, but the position itself is calculated over some function f. And actually, I prepared the simple animation. On the left hand side, we have some blue initial distribution, and then as time goes on, these particles go into the one point. So this is the simplest example. The second example will be containing the stochastic term, Brownian motion, and it will be defined in a d-dimensional case if we define some matrix. And now our drift is position self minus the center of mass. And again, our starting position is time 0 is just u, and we have some push forward. And we can actually explicitly solve such example if we integrate. We can actually see that on the left hand side, if we integrate over all particle or measure m0 like this, then we on the left hand side we have the center of mass. This drift coefficient will be 0 because this is also center of mass, and they both cancels out. And then we have that in such system, actually the mean of all particles, they move like a Brownian motion. So this is what we can, how we can actually get the explicit solution if we differential of ext minus center of mass, then we can actually get the explicit solution for each particle u, and for some center of mass of initial measure. And because our center of mass mt is a Brownian motion, we can see that it evolves also. It evolves actually like a Brownian motion. I have the animation as well for this case. Yes, again, on the left-hand side, we have some measure. The example is d-dimensional, but for this illustration, I used d equal 1, and the initial measure is just takes 3 Gaussian with some parameters, and we can see how the system particles evolves actually. Yes. So this is the second example. Now the all following slides, they will work with such model. We consider it's a slightly simplified one. We consider diffusion coefficient, which depends only on position itself. It does not depend on the measure mt, but the whole system is the same. We have initial points, we have push forward, and the drift coefficient the same. And in further calculation, we need space and distance between two measures. We can introduce to Wasserstein distance. If we have two measures, then the Wasserstein distance is infimum overall couplings between M and the nu, such that such integral is minimized. The next slides will be about what restriction we want to imply on our coefficient, and we consider our coefficient will be d-dimensional. Coefficient sigma is its matrix, and we suppose that for fixed measure our map A is C2, and we have such such bound on the norm of partial derivative operator by some L for diffusion matrix. We can split it in the column. We have the column, and again for each for each column we also have such bound, and we have maximum overall. And because our drift coefficient actually depends not only position, but also on measures itself, we need Wasserstein matrix, and we need bounds for such difference between two measures mu and nu. And such yes, and our particle x, which is started from point u at time t, and it's actually a random map, and we can assign it as t capital T, and we will be using such notation further in this presentation and stock. And what we actually also interested in is the Jacobian matrix over initial position u. It's by the matrix, and based on the previous assumption, such map is actually C1, and also in the book of Andrei Anatolij, under such conditions the solution exists. So such condition implies a solution to such equation. And what was my motivation about this model and this talk, that if we start from some initial measure mu0, and we want to investigate the properties of the measure μt. μt is actually to investigate the mapping capital T itself, and we want some Lipschitz conditions in order to obtain the concentration inequalities, Poincare inequality, Lagrange inequalities, and in order to control it, we actually need control over Jacobian matrix. Because of our model depends on μt, it can be not so evidently that if we write explicitly Jacobian and Jacobian matrix, then our form of Jacobian matrix will not contain the derivative of a measure itself, because our measure depends on all other particles, and we actually have such theorems that if we can actually get the explicit form for Jacobian matrix, which does not contain any derivative of the measure. And this is the theorem of Andrei Dragovtsev and Alexander Weiss by their paper, and also from these assumptions that I mentioned previously, we also can have uniform norm over these coefficients AT and CT. Yes. Okay. What we also want to investigate on the second example that I show, I specifically chose measure that was concentrated on some set. And the idea that if we have some measure mu0 and it has a compact support, and then we want to find the size of the Jacobian of the norm of the Jacobian on this compact set K. And in order to do it, we need some additional assumption about difference of partial derivative of A and a partial derivative of sigma K. They both depend on they are both bound by x minus y. So in order to investigate such properties, we need such assumption. And what if the main theorem is if we take both assumption and take some compact set K, we can actually bound the expectation of such sub of Jacobian. And also we have like explicitly bound for some which depends on two constant, which depends on all other constants that we use in the assumption and compact set K. Okay, I provide only a sketch of the proof. What we actually did, that we choose some integer m, then which is bigger than 2p or 2d, which is useful in further calculations to have it in such a way, but then we can for any p than less than the m, we can also obtain the bound. And firstly, we investigate just the difference from two particles at the same time t, but which starts at two different points, u and v. And as I mentioned previously, the theorem of Dragovcev and Weiss, such even though such they both depends on the measure, but we actually have SDE for them, which can be which can for which we can do the calculation, and we have we can actually do such bound from the with using the initial point difference, and also we can bound the Jacobian itself norm with such. It's only sketch. I miss the whole hard computation, but I provide the main idea how we get it. And then after we but I should mention that what we I can turn back. We have we interested in such in such term which is supremely uniformly over all points in K. But we here we have only a single point, and we need to use Kolmogorov theorem, Kolmogorov-Logi theorem, to have uniform bounds. And to do it, we from Jacobian difference, we can also write SD for it. And you have like this is actually A and D is both matrix. This is matrix multiplication, and this is the most heavily computational part. But again, we also can get so the expectation is less than uniformly less than u minus v in some power m, and using the Kolmogorov Toloki, we can actually find the supremum of such difference divided by u minus v in some beta, which is for here. Then we have bound, and then just choosing any point, we can evaluate it like Jacobian this point and to all other points in the set K. So this is how we get the bound for our KT. Okay, now because we get that for some complex set, we can actually find that we can find that the expectation of Jacobian on that set, we can get the Lipschitz on the set, and we can obtain a lot of inequalities for measure MT. And the first inequality which we can start is the concentration inequality. We have such function from r plus 201, which will non-increasing, and we have this probability on RD, and we say that it satisfy concentration inequality with profile if for any one Lipschitz function f, we have such inequality that the measure of any f one Lipschitz function f means its mean greater than r, it's less than this profile function. And this is I think well-known definition, and now we can actually apply it for stochastic differential equation with interaction. If, for example, we consider some compact set with some initial measure is supported on that set, and we suppose that the initial measure actually satisfies the contrast inequality with some profile function, and fixed t and some sample path, then we obtain μt as a push forward, and define again kt on the convex hull of k, and we suppose that it's greater than 0. So it's exactly the term that we were looking for in the previous theorem. So then our result about measure μt, that for any Lipschitz function g, its profile function depends not on r, but on r divided by L. And the next slide, it will be the proof of this such result. Like actually, we consider that the t is C1 on the convex hull of K by the mean value theorem, but it's not in 1t mean value theorem, but in integral form. We can actually evaluate such difference of such mapping with such with KT over convex hull, and if we denote it by L, then we additionally we consider some function g, which is one Lipschitz. It's the same as in definition, and introduce a new mapping, which is g over tu, and the numerator has L. Now we can hu minus ihv is less than the difference over g, and because G is one Lipschitz, we have just difference between TU minus TV, and as in the previous slide, we mentioned here that this is the L, and TU minus TV is less than the LU, but both L cancels out, and we get such that SU minus HV is less than UV, but it can be that we work on only UV, but maybe we have some other points that will be over such space, and we can use the Mac-Chain extension theorem that said that if we have function like G, which is one Lipschitz and one dimensional, so we can extend it to the whole space with saving its Lipschitz constant. And now it's our assumption that mu0 is satisfy concentration inequality. So now we want to now we want yes, M0 satisfy concentration equality for H one Lipschitz, but for any G one Lipschitz, but we just prove that H one Lipschitz, and because of our measurement is push forward of mu0 under the mapping T, we can write that the integral over mu_t is just integral over mu0 with tu, and by definition of how we define a function hu, we get that the g is just L over mu0, or integral hu over mu0, and now we put it all together to get the final result that if we have our measurement T, which is push forward for any function G which one Lipschitz. Now we for both of this T here and here we use the push forward property, so with composition GT. And as we find here that it's just L over H, and in both cases we have L, and we just divide it by L, and we get that the profile function is R divided by L. Just move L here to the right, and so if we have for some compact set K, we can actually get this supremum KT, and it's L, and then we can actually impose the concentration inequality for this measure mu_t. The next inequality which I want to talk about is Poincare inequality. Again, we have some measure mu0 mu on RT, and we say that it's satisfy Poincare inequality if for every smooth function we have that variation is just integral f minus its mean in the square over this measure. It's less than some constant Cp over norm of power 2 gradient over this measure dm. And the simplest, not the simplest, but a very good example how we can actually get the Poincare inequality, for example, for Gaussian measure. If we in one-dimensional case, if we have some one-dimensional Gaussian measure, and we have L2 space, and we consider Hermite polynomial, then the element f from this space, we can actually write it as infinite series with coefficient Cn and Hn, is exactly this Hermite polynomials. But there is a property that if we differentiate this polynomial, we get a polynomial of index -1 and n minus 1 multiplied by square root of n. And the Poincare inequality, the left-hand side is about variation, and we had f minus mean in the square, but in such representation, mean is exactly c0. So if we want to get variation, we just sum over coefficient starting from 1. But right hand side, we have derivative of f square, and because of the representation using Hermite polynomials and this formula, we get that each coefficient actually is multiplied by n. So comparing this both series, they both started from 1, and each summand is multiplied by n. So we get the Poincare inequality for one-dimensional Gaussian case. This is an illustrative example, and let's get back to transfer of Poincare inequality in our settings. If we have some compact, we have support of mu0 in K, and we suppose that our initial measure satisfy Poincare inequality for Lipschitz test function. And again, MT is push forward. We again define some.
I'm sorry. In this notation CP, what is P stands for?
Coefficient. This coefficient we have the Poincare inequality.
But why you write the index P?
Poincare.
Okay.
Yes, and again we have again we want to evaluate KT. This is supremum over all points in convex hull of our K, and then the Poincare inequality satisfy for version for mu-t with constant CP multiplied by L square. And again we use the same idea that we consider T C1 and on the convex hull of K, and again using the mean value theorem, but now because in concentration inequality, our function J was from Rd to R, and we use McShane's theorem to make an extension to the whole space. But in this case, our mapping is r-dimensional, so we need in the another version of McShane's theorem is actually extension because it's to Rd called Gibbs-Brown's theorem, and again because of the push forward, we can define measure mean, and we can divide the second moments for mu-t and mu0. Okay, and now we have Lipschitz. Our mapping is Lipschitz one, but we would like to get the differentiability, and for this we can use Rademacher's theorem. So we actually get that our t hat is differentiable for almost everywhere, and we can actually use gradient over G. So again, because of the push forward and such bound, our initial variation for mu-t, we just get function g, and for it we apply Poincare inequality, and then again we return to f. So we get that Poincare inequality for such MT, and the last inequality which I want to talk about, it's Talleyrand inequality, Talleyrand transport inequality. If we say that a probability measure satisfies it's Talleyrand transport inequality, if for any other measure lambda, we have that Wasserstein distance of ODP is less than some constant to relative entropy. The relative entropy between the two measures, we suppose that they're absolutely continuous, so we can define the Nicodemus derivative and write it like that. If they're not, they just plus infinity. And the Talleyrand proved for if measure mu is Gaussian, he proved that it satisfies in the case p equal to for Gaussian measure, and then Otto Vitani proved that if measure satisfy logarithmic Sobolev inequality, then we also get a Talleyrand transport inequality. But in our case, we again consider the same step. We have some support of mu0 in K, and we suppose that the initial measure satisfy Talleyrand transport inequality. Measure Mt is push forward, and again we have some L, which is the supremum of Jacobian over all convex hull of K, and then we also get inequality for Mt with constant Ct multiplied by L square, where L square is supreme. Okay. We start the same way, and we consider only the case when the both measure absolutely continuous. But now we need to define another measure at the head, with head, defined as d eta over dmt, the with argument tu over initial measure mu0. What is property of such construction is actually if we want to integrate over such measure with composition of t minus 1, then t minus 1 we just got in the argument of phi, and again we have here tu. Then we can replace tu with some y, and then mu0 goes to mt, and we actually get the integral over d at. So if we can rewrite it in our notation how we defined push forward mt as a push forward of mu0 over t, then this is actually called pullback, because push forward is defined on target space, but here we define it on U, on our initial measures. So we actually return back, and because of such measure, we can actually with head we can explicitly calculate what is relative entropy for it. And in this case, we just write it like explicitly. Again, replace this tu, and we can actually see that if because we just had d eta over d mu t, here d eta, we just entropy between eta and mu t. So our pullback measure is in entropy between eta's head with mu zero is the same as eta with mu t, and it will be useful because now we define eta's head mu zero, and in for Poincare inequality, for concentration inequality, we need some extension theorem for. But in case of Talleyrand, we actually don't need it because we have that function on this the distribution supported on our measure k, and now we consider we can write the Wasserstein distance, and we want if we have coupling between eta hat and mu zero, and let's consider such coupling with composition of t and t minus 1. And in this case, we just using this push forward property, we replace with tx and tw, and we can actually move out the LP. And now, because P is coupling P composition tt minus 1 is coupling between eta and mu t. This is less than the Wasserstein distance between eta hat and mu zero, or some L. And now we use it for square. We have here square. We have eta goes to eta with hat, mu t goes to mu zero. And for this one, we have entropy inequality, and we in the previous slides we've seen that it's actually the same as entropy over eta mu t. So we start with eta mu t, and we actually get eta mu t, and we proved that the mu t satisfy Talleyrand transport inequality with such coefficient. And this was the last functional inequality which I was ready to present. And the main idea of and summary of my talk is that we consider stochastic differential equation with interaction. We have some measure mu zero, and which is concentrated on some port of k, and our stochastic differential equation equations interaction, they define some mapping T, and by controlling Jacobian of such mapping, we can actually control the Lipschitz constant on such support of mu zero, and then we can get this inequality for measure push forward of mu t. Yes, I think it's a final frame.
Okay, thank you. Maybe someone have questions or comments, please.
I wanted to ask about the one of the pictures where you draw the trajectories of several particles. It's one of the first pages. So when we have Brownian motion, yes, this one. So it seems like all the particles have the same shape. Is it necessary, or like in general they can have different trajectories?
What do you mean different trajectories?
Well, I mean, it looks like the shape of all of these trajectories is the same, like they are driven by the same Brownian motion. Is it a part of the construction, or they can have different shapes?
Yes, it's actually one of the
This
main.
is because of the equation.
Yes, there is another example of this equation with interaction, Makin-Vlasov, and there in their case, each particle has its own Brownian motion. But stochastic differential equation, they have one Brownian motion for all particles. So
Thank you.
yes.
Other questions, please.
I might have a question. Could you please return to the original equation you're working with? Here. So a bit lower.
Yes,
A bit
yes,
lower. Here you have sigma that depends only on the position but not on the measure. What is the intrinsic reason for this choice of sigma?
Actually, I started with constant coefficients, and I gradually add complication to it. And one of the steps was I just considered the drift fully depends on the MT, but sigma depends on position. So
Because it feels everything should be doable when sigma is a general one. You might need functional derivatives when writing the equation for the difference in the result of Dorogovtsev and Weiss, but as it feels it should be possible to generalize it to a general stochastic differential equation with interaction.
There might be a difficulty that the measures may be not absolutely continuous for different yield.
I see. I see. So you need additional assumptions still. I see.
Well, I don't mean that you should not try it.
Yes, thank you. Thank you very much for this clarification.
Okay. Other comments, please? Let me also do some comments. Firstly, I have to say that this talk is, in some sense, continuation of our attempt to understand how the interaction in the equation with interaction. Maybe on this slide you see coefficient A, which depends on the measure and the position of the particle. The same can be written as a diffusion coefficient. So how the interaction implies some properties of the measure-valued solution. In 2005, we with Maria Karlikova proposed so-called shift compactness, where we propose such conditions on the interaction term that the measure-valued solution can float around the space, but still the measures, if we shift them, for example, on the center of mass, organize a compact family. So the mass don't spread along all the space. Then today we see how one can propose not quantitative but qualitative estimation for this concentration phenomena. Of course, as it was mentioned by Alexander, we have to be careful when we generalize the diffusion coefficients to general case. Actually, the reason is because we have not good Poincare inequality, for example, for singular measures. Yeah. We just need to have some measures which looks like more or less a Gaussian measure. And here the history is very long. Let me mention logarithmically concave measures. I also tried to generalize Poincare inequality for restriction of Gaussian measure to some arbitrary open set in Hilbert space. It can be proved, but this is slightly another story. We just want to understand how the mass is spreaded or concentrated during the time due to the interaction. And I hope we will continue this work. This is just initial case because as you will see, the main problem here is the following. Yes, we can control this Lipschitz constant due to the idea that maybe this derivative of the flow with respect to the spatial variable is bounded on the compact set. But if it is unbounded, if the set is unbounded, we know examples of Sheitsov and Mohammed that even for good stochastic differential equation, the flow cannot be Lipschitz with respect to spatial variables under good coefficients. So here we have to control the growth of the flow. And again, our idea is to control it in connection with the properties of the interaction. So this is the aim of this project, and I hope that Kirill will continue with it. That's all what I wanted to say. Maybe someone have another comments, questions, please.
Well, I wanted to ask if there is any hope to extend it to infinite the dimensional phase spaces.
Actually, it is what I mentioned, that I tried and I was successful to prove Poincare inequality for restriction of Gaussian measure on the open set. It is very close, by the way, to the notion on polynomially non-degenerated measure. I proved again for Gaussian measure restricted on the open set, but some of PhD student of Vladimir Bogachev proved it for general Borel set. So you are right, and I think that it can be done because I constructed equation with interaction in infinitely dimensional case, and I think that at least we can start with Poincare inequality.
Yes, from the proofs that I saw, it seems like it can be done.
You see, we have to be very careful. We have to find something instead of Rademacher's. Yeah. So we have to use some approximation like finite dimension, like Galerkin. Yeah. But yes, you are right. Maybe it can be done. Okay, another questions, please. Okay, if not, then thanks everybody to speaker for the talk and our audience for discussions, and maybe Katerina, you know who will be the next speaker.
Yes, the next speaker will be Maria Belozorova.
Okay, and please pay attention to the announcement of the seminar because this is some change in our schedule because of disease of Nasir Hanihadjayev. His talk will be cancelled, and instead of his talk, we have the talk of Maria. It is shifted 2 weeks early. Okay, for today that's all. Thanks everybody for attention and bye.
Thank you and bye.
Bye bye.